I want to talk a little bit about kinetic molecular theory because kinetic molecular theory is one of the ways that chemists understand matter in general. This is just kind of one of the fundamental theories that we've used. It's been around for a very long time, kind of since the birth of chemistry. When they were first studying gases and the gas laws, they were looking at the movement of particles. And so they came up with these ideas that said that everything is made up of particles. These particles are always in motion, and this random motion of particles is going to give these systems certain characteristics. And so this really came about because of the study of gases. As early as Robert Boyle, for example, one of his lab assistants was one of the first people to postulate kinetic molecular theory, a guy by the name of Robert Hooke. Some of this kinetic theory is credited to Isaac Newton, and it's been kind of formulated and reworked through the years as we've understood more and more about, atoms and particles and the interaction between those particles and the forces that govern particles that are this small. And so this kinetic molecular theory has really evolved throughout the course and the history of chemistry, but it really started with the study of gases. And so it sounds a lot like it's related to gas particles, and if it does, it's because it is. It also sounds a lot like atomic theory, which was built slightly later than this on this idea in the study of gases. So let's kind of walk through some of the postulates of kinetic molecular theory. First of all substances are made up of particles, and this is where it kind of sounds like atomic theory, right? Which starts off with all substances are made of atoms. Well, the particles could be atoms, they could be molecules. When we're talking about particles, we're just talking about teeny tiny things. Now, when we think about them in terms of gases, it's easy to sort of visualize these little gas molecules pinging around, but these particles are always in motion, and that's regardless of what phase it is. So even though we think about this and it was built around gas as a phase, particles even in solids and liquids, right? The liquid in my ink, the pen, the solid pieces of my pen here, the particles in my hand are always in motion, right? Everything is always moving, except at absolute zero, which is 0 Kelvin. Now this motion is random, and the particles are going to move around in straight lines until they bump into things. So I kind of like to picture them like pool balls on a pool table. They're going to move around in straight lines unless they hit into or collide into something else. And kinetic molecular theory says that when these particles collide, the collisions are elastic, and what that means is that the energy is conserved in that process. Now, the energy that we're talking about, the energy of moving particles, is kinetic energy, hence kinetic molecular theory, right? So kinetic meaning movement or motion, molecular referring to the particles. And the average kinetic energy of all these particles is going to be directly proportional to the temperature, or that is to say, if the temperature increases, then the motion increases. We'd say that there's a direct relationship between these two variables. As one of them increases, the other one increases. If my temperature was to go down, that would slow things down a little bit, and the motion would decrease. Now this has implications on, again, I kind of keep coming back to gases, but it has implications on all the different phases of matter. I'm going to say that it helps to define the phases of matter here. And what I mean by that is that depending on how free these particles are to move around, then we can classify matter as a solid, a liquid, or a gas. So solids have the least freedom of motion of their particles, right? If we're kind of visualizing a solid, it's sort of tightly packed particles. When we're thinking about the motion of these particles or the movement of these particles, it's really vibrational, right? So they're still moving around, but they're kind of vibrating back and forth because they're sort of caged in. If I'm just looking at this one particle here, and I'm picturing this in 3D, so particles kind of behind and in front of, then this one is sort of caged in by everything else. It's vibrating and moving around, but it's not going to just shoot out, right? Not in that position anyway. So solids have the least freedom of motion, and that helps to define them as solids. That's how we recognize them as such. Whereas liquids are a little more fluid, so their particles have a little more space between them. So picture that this is in a beaker maybe. So we have a liquid here with these particles. Those are my motion lines. They're moving around. There's some space between them. There's flow, right? These particles can move past each other, which allows for the fluidity of a liquid. And then gas particles are just, there's so much space between them relative to their size. You know, they're moving around. They're barely interacting with each other because they're just so tiny. They're moving so fast. And so they're kind of zipping around. And we can recognize gases then by that space between the particles, the speed at which they're moving. And they, like all the other particles that we're talking about here, are moving in straight lines until they run into or collide with other particles. And again, that energy, if we're thinking about it in terms in the context of energy, the energy comes from the energy of motion, right? The particles themselves also have some sort of potential energy depending on what they are, but that energy of their movement is going to be conserved whether they run into the side of the container or they run into each other, etc. So this is a fundamental way that we as chemists, we as scientists in general, understand matter. When we think about the different phases, it all comes down to this kinetic molecular theory. Everything is made of particles. These particles are always moving around. The motion is random, but in straight lines. And the energy of this process then is conserved even when things bash into each other. And we have to make those assumptions, and that's going to lead to other assumptions we can make when we get into things like the ideal gas law or some of those other types of things that are going to rely more heavily on the movement of these particles when we start to tweak different variables like the temperature. We increase the temperature, we increase the motion and the speed of the particles. That's going to have implications on things like pressure. It's going to have implications on things like volume, because we know that gas particles are compressible or expandable, so they can fill up a larger space or be compressed down into smaller ones. So kinetic molecular theory is really important for us to kind of understand and visualize the different phases of matter and to understand the relationship between the temperature and that motion, and then also the energy that comes about because of that process. So that's a little bit about kinetic molecular theory. If you have any questions, as always, reach out. Otherwise, I'll talk to you again soon.